This video will be on the resolving power of a telescope, how well it distinguishes features on things. And the number that we end up putting on this is how the angle at which it can still distinguish two objects. If the two objects get too close together, they're blurred together. I'll start by showing you a picture that I took in the classroom last year. I shined light from a green laser through a small hole that I drilled in an aluminum plate, and it was maybe 1/8 inch or maybe a little bit less than that as far as the thickness of the aluminum plate. And I did not get a single round dot when I did that. I had it reflect off of a couple of mirrors and shine up on the screen in the front of a classroom. And you can see the complicated pattern that you get from that, this kind of bullseye pattern. The center of it is actually much brighter than the rest of it, but it was so bright that it swamped the light sensor in the camera that I was using, and so you don't see something like that. This is a bit more complicated than it would be typically. Actually, because of the thickness of the plate, I was actually getting some reflection off of the sides of the hole in the aluminum plate, and so that made this image a little more complicated than it would otherwise be. And it doesn't look like it's perfectly round, probably because of the way I reflected it off of the mirrors. But that's the complicated pattern you get. Here's a sketch of the mathematics of this. The one on the left shows the intensity. The very center is the central bright point in the thing, and something you can see is that it drops down to 0 at a certain distance from there, and then it comes back a little bit, but that secondary peak is only about 1% or 2% as bright as the central peak. And then on the right shows more of a three-dimensional pattern that you can produce with a graph. This is just something that's a little simpler to look at. This is what's called an Airy disc, and A-I-R-Y. It's what that pattern happens to be. We call that a circular diffraction pattern. You actually use this at times in optics. When you're grinding a telescope mirror, you will aim the telescope at a bright star and defocus the image slightly. And if the Airy disc that you see is nice and circular, then you have a nice telescope mirror with circular symmetry. And if it's not, you've still got some work to do on the thing. So that's something that's used. The resolving power is the minimum angular separation between two objects for which you can resolve the two objects. And that just means that you can tell that there are two objects. When they get too close together, you can't. And so we'll have to deal with that. And this is a power where the smaller the angle is, the better your instrument happens to be. And that means the more you can see fine detail in things. And there's an equation for it, of course. The equation looks like this: theta min. Theta is that Greek letter, looks like an oval with a line through the middle of it. And it's a Greek letter that's commonly used for referring to angles. So, and I've got theta min on this. It's the minimum angle that you can get. And it's 1.22 times the wavelength of the light divided by the diameter of whatever it is you're using to look at it. However, for comparing two telescopes, we can use a simpler version just fine. And we're just going to use that the theta min is just equal to the wavelength of the light divided by the diameter. And again, features of it: theta min, it's the minimum angle the instrument can resolve. Lambda is the wavelength of the light, and d is the diameter of the instrument. We'll compare some of the same instruments that we did yesterday. I'll call it RP, and I'll put the RP for the big on top, resolving power that is, RP for the small on the bottom, and this would end up being lambda over the diameter of the big one divided by lambda over the diameter of the small one. Now, when you divide one fraction by another, you invert and multiply, so I'll have lambda over the diameter of the big times the diameter of the small over lambda. You can see the wavelengths divide out, and I just get the diameter of the small over that of the big, which is 7 millimeters over 50 millimeters. And the millimeters divide out, and you get 7/50, or 0.14. And that tells me that whatever angle the pupil of the eye can resolve, the binoculars will be able to resolve an angle that's only 0.14 times that. I could also do the reciprocal, and if I did it, the mathematics would be identical, except I'd end up with the diameter of the big one over that of the small one. And if I do that, diameter of the big over the diameter of the small, I'd end up with 50 divided by 7, and so I get about 7.1 when I do that. And that tells me that whatever angle you can resolve with the big one, the angle that you can resolve with the small one is going to be 7 times bigger. So if I just sketch that very quick here, maybe that's the angle you can see with the big one, an angle 7 times that big, and I'm way exaggerating the size of these angles here. That might be what the small one can resolve, when that could be what the big one resolves. Anyway, you can do these things either way, and they work out pretty well. Let's see, compare the resolving power of a binocular with a 50 millimeter diameter objective lens with that of an 8-inch diameter telescope. And I'm going to go ahead and do what I did before with the resolving power of the big one divided by the resolving power of the small one. So these will both be working with the same wavelengths of the light. Invert and multiply, the lambdas go away, and you end up with the diameter of the small over the diameter of the big again, and work through the math slowly if you need to see that. But anyway, we'd have the, not 500, but 50 millimeters on top and the 200 millimeters on the bottom, and that's 0.25. The millimeters divide out, and 50 over 200 is 0.25. And that means that the large telescope can resolve things that are only 1/4 the distance apart that the small telescope can resolve, and distinguish them as two objects. Now I'd like to finish up with one that's a little more complicated. We want to compare the resolving power of the Hubble Space Telescope, which works in the visible spectrum, with the James Webb Space Telescope, which uses infrared light. So this time I'll have to distinguish between those two different wavelengths. We'll have the resolving power of the JWST divided by the resolving power of the Hubble Space Telescope, and that will equal the wavelength that the James Webb Space Telescope is using divided by the diameter of it, and then the wavelength of the Hubble Space Telescope divided by its diameter. And as before, when you divide by a fraction, you invert and multiply, so I'll get lambda for the James Webb Space Telescope divided by the diameter of that one times the diameter, remember I invert the bottom, diameter of the Hubble Space Telescope divided by the wavelength that the Hubble Space Telescope uses. And this will equal, let's see, for the James Webb Space Telescope, the wavelength it's studying, actually it has a whole spectrum, but I just picked one in the middle of it, will have 2.5 times 10 to the minus 6th meters. Yeah, I'm going to have to convert all these wavelengths to meters. The diameter of the James Webb Space Telescope is 6.5 meters. And then the diameter of the Hubble Space Telescope is 2.5 meters. And the wavelength that it uses is 550 nanometers, which I have to write as meters, so I'll just do 550 times 10 to the minus 9th meters. And I get about 1.75 or so, something like that. I've only got two significant figures here, so I'll just stick with that. And what this means is that the James Webb Space Telescope doesn't quite have the same resolving power as the Hubble Space Telescope. It's actually a little bit worse. Remember, I put the James Webb Telescope on top and the Hubble Space Telescope on the bottom, and the resolving power of the James Webb Telescope is about twice as big, 1.7 times as big as that of the Hubble Space Telescope. So not quite the same fine detail, but still not bad. The Hubble Space Telescope does pretty well. And the James Webb Telescope has been designed to study infrared light instead, and so it'll be looking at a whole part of the spectrum that the Hubble Space Telescope can't touch. This is a simulation of how resolving power can make things look much different. And on this, I have the ability to change the effective diameter of the aperture on the telescope, or whatever the instrument happens to be, and then change the separation of the two light sources. And it also shows the light curves that are produced by the light from the different sources. If I decrease the diameter, I'm going to turn off the light curves, they may just confuse you. If I decrease the diameter of the instrument that we're looking at these two sources with, or decrease that diameter, excuse me, at some point you can't tell that there are two sources anymore. And so that shows the effect of decreasing the diameter. Although if I increase the diameter, you can see those two sources are easily split if we use enough diameter on here. I can also decrease the difference or the distance between two things, and if I put that distance down to 0, well, they're one source, but I'll put it at kind of an intermediate one here, and then things get tough to tell apart at about this point, actually. And then here they almost look like a single merged object. So, but that's just an animation, but it shows what happens when you change the diameter, decrease the diameter, you get so you can't see such fine detail anymore. And as you increase the diameter, you can see more detail. Not a lot of detail to be seen in these, but at least you can tell that they're two different light sources if you have a large enough diameter. Well, after this video and after the video on the light gathering power, you should now understand why they make telescopes so large. Here's a mirror that was manufactured for the Large Binocular Telescope, and it's about 8 meters in diameter, but you can see it dwarfs the people in the picture. We get more light from a larger diameter, and we also get the ability to see detail better. You may wonder why it's called the Large Binocular Telescope. Well, that's because they made 2 of these. There's the Large Binocular Telescope with the mirrors installed, and this is someplace that I'd like to see sometime. Maybe if I start hunting on the internet, I could find a way to get a tour of it.